All right. Good morning, folks. Today is day 2 of our Unit 9 on acids and bases. And today we're going to take a little bit of a detour and talk about dilution. Now, dilution is a common lab technique that frequently applies to acids and bases. Because usually if we're working with an acid in a lab, we'll receive a very concentrated acid solution from a supply company. We're talking like 12 or 18 molar in terms of like maybe getting some HCl, some hydrochloric acid, or sulfuric acid, H2SO4. And so in order to use a more appropriate concentration, we have to take a small amount of that concentrated or stock solution and add a bunch of water to lower its concentration. So, we don't change how many moles we have of the acid, but by greatly increasing the volume of the solution, we drive that molarity or concentration down. So our formula for this, and this is a formula I would probably expect you all to know, is M1V1 equals M2V2, where it really doesn't matter which side of the formula is which, but typically our M1V1, that kind of represents our stock solution. That's going to be our solution with that higher initial molarity. It's going to be the more concentrated side. And then usually our M2V2 side is going to be our dilute solution. It's going to be the one with the lower concentration, the side with the lower molarity. Again, it really doesn't matter which side is which, but typically this is kind of like how I like to approach this sort of problem. And kind of one thing to note before we solve some problems here on page 3 in Unit 9, probably should have led with that, sorry, is that molarity, we need the same unit there. That's pretty easy because capital M is just molarity. We only have the molar unit for that. And then our volume unit also needs to be consistent. So as long as both volumes are liters, or even both volumes could be milliliters, we'll be okay. All right, so let's try number 2. So number 2 asks, what volume of 0.250 molar potassium chloride is needed to make 100 milliliters of 0.1 molar potassium chloride solution? So, okay, as I look at this, I see, I have a molarity here. And notice it's my higher molarity, so that would be my M1. So I would have my 0.250 molar KCl. And I want to know what volume of that is needed. So that tells me I don't know V1. And I want to make 100 milliliters of that 0.01 molar solution of potassium chloride. So my M2 would be that smaller concentration of 0.1, or I should say lower concentration of 0.1 molar. So notice I've plugged in, and then to do the math, I always just divide both sides by whatever is next to my x. So I'd multiply both sides by 0.250. Sorry, divide both sides by 0.250. So 0.1 times 100 divided by 0.25. And then I get my V1. And let's check sig figs here. I should have, I think, 3 sig figs. 40.0. And then this is volume, so my volume units just, again, like we said earlier, have to match. So my V2 is milliliters, so my V1 would also be milli. I know that's a little sloppy there, but that's milliliters. So in other words, what we do, if we had to make this solution, I'd measure out 40 milliliters of that 0.25 molar potassium chloride, and then add water to get that final volume of 100 milliliters. All right, let's try a couple more. Number 3. Concentrated sulfuric acid is 18.0 molar. So what volume of 18.0 molar solution is needed to make 2 liters of 1.0 molar H2SO4? Okay, so again, concentrated, I like to use that as my starting solution. So 18.0 molar, and we want to know V1 is going to equal our M2 There we go. Sorry about that, just struggling a little bit this morning. So that would be my setup. So again, we would just divide both sides by 18. So 1 times 2 divided by 18. And I would get my V1 as let's see, how many sig figs? I think 3 sig figs. Yep, 0.111. And then volume units have to be consistent. So V2's in liters, so my unit would be liters. So again, something like this, I would measure out my 0.11, or right at 111 milliliters of my concentrated sulfuric acid, and then I would add enough water to get to that final volume of 2 liters. So I'd wind up with 2 liters of that 1 molar sulfuric acid. Let me see if I can make this a little thinner. Ooh, let's try a sparkly one next. All right, let's try number 4. So number 4, we're told concentrated hydrochloric acid is 12.0 molar. If we have 250.0 milliliters of 12 molar solution, if we dilute it to 750, what is molarity of diluted solution? Oh, okay, a little bit different. So we have our concentrated molarity. So we have 12.0 molar. And we're told that we're taking 250 milliliters of it. And we want to know, okay, I'll stop after this problem. Galaxy's not working out too nice. We want to know the new molarity. We want to know M2 if the final volume is 750.0 milliliters. So again, the reason I picked M1, that's what I'm starting with. V1 is there, that's what we're starting with. And we want to know my new molarity after we add 500 milliliters of water to get up to that V2 of 750. So we just divide both sides by 750.0. So 12 times 250 divided by 750, and we would get an M2 of 4, but we have to watch for our sig figs here. I think we need 3, right? Is 3 or fewest? Yeah, 3 sig figs in 12.0. So that resulting molarity would be 4.00, and then throw that capital M on there, or you could underline it, or you could write moles per liter as our unit for molarity. So not too bad, right? As we take a look at M1V1 equals M2V2, it's really not that bad of a formula as long as we keep track of everything. All right. So let's try number 5, and that'll probably be the last one. So number 5, we have 2 liters of 0.8 molar potassium nitrate solution. Is prepared or are prepared using 162 milliliters of a more concentrated KNO3 solution. What is the molarity of this solution? Okay, this one is a little bit of a curveball. So again, usually I like to use my M1V1 side as what I'm starting with. So as I take a look at this problem, we're told that we have this more concentrated potassium nitrate solution. We want to know what that is. So again, as I look at this, I want to know M1. We're told we have 162.0 milliliters of that more concentrated solution, and we use it to make that 0.800 molar solution with that final volume of 2.00 liters. So that's our setup. Again, you could have done M2V2 as you could have done M2 as our unknown and 162.0 milliliters as V2. It's just kind of by convention, I like to have my M1 V1 side be my more concentrated side. So as I look at this, I think I'm ready to solve it, but what's the problem here? Think about it. Oh, my problem here is that my units are different. I can't have two different volume units here. So I'm going to change my V1 to liters. So I'm going to divide by 1,000, which is the same as moving my decimal 3 to the left. So my V1, I'm going to write as 0.1620 liters. Now I'm going to go ahead and divide both sides by 0.162. So 0.8 times 2 divided by 0.162. And I'm going to get my initial concentration as, see, sig figs, I think 3 of them, right? Yep, 3 sig figs, 9.88 molar as the concentration of my stock solution. So that's dilution. Try your hand with the rest of this page, with with number 6 on 3 and the rest on page 4. And this is your homework that's due tomorrow.